Hello everyone, I'm Paul and today we're solving problem 1123, lowest common ancestor of deepest leaves. The description of this problem might be a little bit confusing, so we will focus on the title, okay? For example, let's say we have a tree, so we want to find the deepest leaves, which in this case is 2 and 3, and after that we need to find the common ancestor of those leaves. So in this case it's 1. And the same logic applies if we had only one child. So if this was the case, we'll have a tree of 1 and 2. Our deepest leaf would be this one, 2, and the common ancestor of the deepest leaf would be 1. And finally, if we had, for example, only one node, our deepest leaf would be 1, and in this case we would have to return 1. Now let's say we have this. So our deepest leaf here is 3, and the common ancestor for this leaf is 2. Okay, so here is where you don't have to confuse this part. At first I was thinking that I had to return 1, but that's not the case. So from the deepest leaf we need to find the lowest common ancestor. Okay, so now let's see how can we solve this. To solve this we need to implement what's called a post order traversal. So what this means is we are visiting every node always from the right side. We start from the root and we go to the left, okay? And we want to visit every node that we touch from the right side, okay? So the first one will be the 6. Why? Because we go over here and we touch the 6 from the right side, so we visit the 6. Then we continue over here, we visit the 7 because it's the next node we can touch from the right side. We continue, visit the 4, then the 2, then the 5, and then the 0, then the 8, the 1, and finally we visit the 3. Okay, so for each iteration we're trying to get 2 values, a count and a selected node. Okay, the count will be the depth that we can get from bottom to top, and the selected node will be our temporary result. So let's see how this works. Let's say we're here at node 6 and the count for the left side is 0 because we don't have any nodes, and the right side is 0 also. When the counts are equal, we will take any of those and add 1. Okay, so in this case it's 1, and we will take the current node, which is 6. Okay, and we will do the same with the next node, which is 7. Here the count will be 1 and the selected node will be 7. Here the count will be 1 also, the selected node is 4. Then we continue, and here we are at 2. So at the left of 2 we have a count of 1, and at the right we have a count of 1 also. So when the counts are equal, we said that we are taking any of those counts plus 1. So here the count will be 2, and the selected node will be the current node, which is 2. Okay. Then we continue and we are node 5. In this case, the right count is 2 and the left count is 1. So when right is greater than left, we are taking the right node as the selected one. So here the count will be the count from the selected side plus 1, which is 3, and the selected node. In this case, as we said before, and the right side is bigger than the left side, so the selected node is 2. Then we continue with the post-order traversal, and we find this, and we find the 0. So here for the 0, we'll get a count of 1, and the selected node is 0. Here we get a count of 1 also, the selected node is 8. And then we are here at 1, and we have a count of 1 to the left side and a count of 1 to the right side, so the count is 2, and the selected node is the parent of the 2, which is 1. And finally we are at the root. Our count on the left side is greater than the count on the right side, so the count will be 4 and the selected node will be 2. So finally this is our selected node, which is 2, and the corresponding subtree is this one. So this is our final answer. And finally, about the complexity of the solution, we are iterating over the 3 ones, so time complexity will be big O of n, and space complexity will also be big O of n. So now let's code this up, and hopefully you will get the idea. So first we need to create our post-order traversal function. So we will create it with def dfs. This will take 2 values, a distance and a node, and this will return 2 values also, a distance value and our selected node. So first we will say if there's not a node, we want to return the distance or 0 and none. So if we will start this function with a v of 0, so if we find no node, we are returning 0 and none. Then we can call this function fs. We want to take a distance plus 1 for the new distance, node that left, and dfs on the right side. And each one of these will give us 2 values. One is the left distance and the left selected node, and the right distance and the right selected node. And now we will say if the left distance is greater than our right distance, we want to return our left distance plus 1 and our selected node on the left side. Else, if our right distance is greater than our left distance, we want to return our right distance plus 1 and our right node our selected node on the right side. And if our two distances are equal, else we want to return any of those distances, let's say right distance plus 1 and the parent node. So our parent node is here, node, and the child nodes are here, left node and right node. So if any of both sides is bigger than the other, we are returning the node on the winner side, and if both sides are equal, we are returning the parent node. Okay, and finally we can return the fs of 0 root, and as we said before, this will give us two values, so we want the value at index 1, and I guess this should work, and it works. This problem might be tricky at first, especially if you have never seen nothing like this. So if you are still confused about this one, I recommend you to watch this video again. If you found this useful, please drop a like and subscribe, and see you next time. Bye bye.